In this video, we're going to talk about the heap data structure. Now, the heap data structure is a special type of binary tree, and there's also two types. There's the minimum heap and the maximum heap, and we're going to discuss both, and we're going to discuss all of the common operations that we would use for a heap. So this is a minimum heap, and the reason it's a minimum heap is because the parent is smaller than the children. So the minimum heap has the heap property that the child has to be greater than or equal to the parent. And then you've also got a maximum heap where the maximum value is at the top opposed to the minimum value. And in the maximum heap, all of the children have to be less than the parent. So basically the reverse of what this is here. So 7 could be at the top, then 6 and 5 and so on. So we're going to take a look at the minimum heap first, and then we're going to extend that to the maximum heap with just a few tweaks. But before we do that, we just need to dive into a couple of observations that we can make with the heap. Now, the first thing to note is because we have a binary tree structure, we can see that basically the number of nodes essentially doubles on each level. So there's one node here, then there's 2 nodes here, then there's 4 nodes here, and so on. And we can use that observation to sort of find the parent or the one of the childs, either the left or the right, if they exist. So basically, and we're saying that this first element here has the 0 index, this has the first index, this is the second index, this is the third index, this is the fourth index, this is the fifth index, and this is the sixth index. So indexes are 0 based because we're going to implement this with the array data structure under the hood, and we can do that. You might think that we might need to use a tree data structure to do this, but we can actually implement this with an array because of the fact that we can take this consideration that, you know, there's a left and a right child and the tree's filled left to right. So we can actually make use of that to derive a few things. So one of the things we want to derive, say we're on the, we have this value 3 here. We want to be able to get the parent. So let's consider both 2 and 3. How would we get the index? If we know the index 1 here, basically what we can do is we can say, well, because we know that this row has double the amount, essentially if we were to halve that value, you know, we'll get the one before it. So actually I might explain this the other way on, in the sense that, let's say we have this index 0 here and we have the value 1. How would we get the value 2 or 3 or the corresponding index? So from the index 0, how would we know that the left child is 1 and the right child is 2? And we want to figure out how to do that programmatically, so whatever node we're on, we'll be able to get the left and the right index. So then we can have a lookup to the children. So let's say we're on this node here, this 0th node. Basically, if we want to get this left child here, essentially what we can do is we can double the index, in this case it's 0, and then we can add 1 to it. So I'm just going to put a formula here on the left side. So I'm just going to say LC, which stands for left child, is going to be equal to the 2 times the index, so 2i plus 1. And of course, the right child, since we've got a binary tree and it's filled left to right, we're only going to need to add 1 to that because the right child is just 1 index to the right. So the right child we can find using 2i plus 2. So let's actually see this. So for the case 0, double 0 is 0, but then we plus 1. So then they'll get us the first index. The right child here, 0 plus 2, that's going to get us 2. And then let's do it again one more time for this second value here, this first index here. If we plug in 1 into the formula here, based on the fact that a binary tree, essentially each of the number of levels doubles each time. If we double this value here, we get 2. And then if we add 1 to that, we get 3. And if we add 2 to that, we get 4. And then one more check. Let's see the number 2. If we double 2, we're going to get 4, which will take us to here. But then we can just add 1 to that and 2 to that to get the left and right child. So that's just a simple observation, and that formula holds correct for any binary tree to get the left and right child there. So you can actually test it out for yourself and confirm that for yourself. But that's just a mathematical fact there. Another thing we might want to do is we might want to go the other way on. So let's say we're on a child 2 or 3, we might want to be able to get to the 0th index there. And we can actually do that by just reversing the formula here. So if you look at this here, we can see we got this 2i plus 1. We could essentially do the reverse of that with a little bit of algebra. And we could just say that the parent node is going to be equal to, so if we're considering us that we're the left child and the index is going to be the parent, if we sort of take the left child, we minus 1 to get rid of that 1, and then divide it through by the 2 there, we'll have the index by itself, which is the parent. So that's going to be the I, if we're considering the index as the left child now, we can say the index that we're on minus 1, and all of that divided by 2. So we're dealing with integers here. So let's actually just do this check here. So 1 minus 1 is 0. And this should be a divided by sign here. Divided by 2, not times 2. So 0 divided by anything is going to be 0. Let's consider this index here. 2 minus 1, that's 1. And then 1 divided by 2 is going to be half, right? So we're just going to need to take the floor. So I'm just going to do f of all of that. Because basically we've got a binary tree and we're going to have fractions of halves. So half, 1, 3 over 2. And if you get a fractional value, which is factor of half, we're just going to round down. And that'll just always get us the parent there. So they're just some observations that we're going to make use of. Now, the actual heap property, the actual operations that we're going to have on the heap is we're going to want to be able to insert into the heap. We're going to want to remove it from the heap. And while we're doing that, we're going to want to preserve the heap property. So again, this is the minimum heap, and you can see that the child is always greater or equal to the parent. So this could be a 1, for instance, this 2 here. And then the max heap's the other way on, where the child is always smaller than or equal to the parent. So let's just think about how we would go about actually being able to insert or sort of remove from this. And it's actually, if you, let's say you want to insert the number 1 here. Well, basically, the first thing we do is below this 4, at the very end, so after the 7th, at the end, we insert like a 1 at the bottom here. But then that no longer, which is the next available spot in memory, the end of the array. But we see that this no longer satisfies the heap property because, 1 is less than its parent. So basically we want to get a 1 to this sort of spot here. So what we need to do is we need to check the parent, and if that's less than, if that new element that you're going to put in is less than the parent, you can swap them around, but then 4 and 1, they'll be swapped. And then this one will still be in the wrong spot. So then you need to sort of recursively go up the parent and compare them. And if that's, until you get to the break condition where the parent is no longer bigger than the child. And since it's already sorted in the heap property when you insert it, you can sort of ensure that the heap will be in heap property will be conserved after you've added it in and you've swapped the things around. Because what you'd get into that situation is once you've gone up the chain, this would be 1, this would be 2, and then there'll be a 4 below it. So that all stays well and good. So that's how we go about inserting something. So let's just talk about how we would conceptually remove something. So when we remove something, well, firstly, the easiest case is removing the last element here, because everything's already sorted. If you remove that, basically all the rest of the elements in the array or the elements in the heap, they'll still be sorted in accordance to the particular heap property that you're doing. I.e. if you're using a min heap or a max heap. In this case, we're looking at a min heap. But if you get the case where you're removing, let's say you remove this element 3 here, basically the process is, firstly, you swap 3 and 7 around. And you might think, well, why would you do that? And basically, the reason you do that is because when you swap the 7 and the 3 around, you can actually pop the 3 off here. So the 3 would be here, and you can pop that off. And you know that a pop is an O of 1 operation. So there's a time complexity performance boost to that. And then we're sort of leveraging the fact that we're using a heap data structure, which allows us to, since there'll be a 7 here now and a 3 here, it'll be out of order. So essentially a 7's here and a 6 is here, and that violates the heap property for the min heap property, because this 7 is parent is greater than its child here, 6. So basically, if that's the case, you can perform an operation called heapify, which basically it takes that index and then it checks the parent and the child's related to that index adhere to the heap property. So basically, if your array or your heap ever violates the property, the heap property, the heapify method will reorder things back into adherence with that. So that's the conceptual overview of the heap. Let's take a look at the code of how we can implement the heap. So I'm going to start by having an abstract class here, and I'm going to call this heap, and I'm having an abstract class because I'm going to implement a minimum and a maximum heap separately. So both heaps, they're going to have obviously the heap array, and we're going to do the numbers, the number array. So we also want a constructor, and the constructor in TypeScript, we can say this dot heap array is going to be equal to an empty array. And that means when we instantiate it, it will have no elements in the array. So we'd probably want to insert something to start off with. But before we do that, let's just go ahead and implement all of the helper functions that we were talking about. So the first one was the getting the parent index. So I'm going to have a private method for this one here, and I'm going to call this get parent index. And the reason we have this as a helper is it's going to be useful within some of our insert, remove, and heapify methods. So basically, to get the parent index, as we saw in the conceptual overview, we just want to return the floor of the index minus 1, and then all of that divided by 2. So we're going to need to take the index as an argument, and it's going to be a number, and then we're going to get the parent index, which is also going to be a number. So that's how we can get the parent index. So now I'm going to just copy that down, because we want to get the left child index as a helper as well. So that also takes an index and returns an index. And as we saw, this is just going to be 2 times the index. And since indexes are 0 based, we can just go ahead and we can just plus on the 1 there. And then we can copy this down one more time. And then we can go ahead and we can get the right child index. And we just need to add 1 to that, because the right child is 1 spot to the left. So we can just go ahead and add 2 there like that. Another helper that might be handy is just to see if all of these exist, because you might be at the top node and there might not be a parent, for example, or you might be out on the bottom level of your tree and there's no more children. So we'd want to be able to break from a loop if we're in a loop, for example. So basically this is going to be pretty simple. We're going to actually sort of leverage the get parent index here. So we're going to return this dot get parent index, and essentially if we pass in an index and you get the parent index, if that's greater than equal to 0, we're going to have a parent. If you're on the 0th element and then you try and get the parent index, this will return something that's undefined. So like for example, if you're on index 0, 0 minus 1 is minus 1, which is a negative number. So since that's not a parent, well, it's not, you're at the top, there is no parent of the parent at the top of the root, that will return false. So that will be has parent has false. So I'm just going to copy this down for the, I'm also going to have this same sort of helper for the left child here. So has a left child, same sort of thing, except this time we're going to utilize the get left child index here. And if this index is less than the heap array length, that means that doesn't exist. And similarly, has right child, we're going to leverage the get right child method here. If that's less than the heap array length, which we've defined here, then there's no right child. So just to think about that, imagine that there's just one node in a tree, the index 0, element 1, you pass in the index 0 here, and then you try and get the left child here. So essentially you're going to get the index, which is going to be 1, but the length of the array is going to be 1 as well. So 1 is not less than 1, and a similar sort of thing will happen here. So that'll return false in those cases. So we've got a bunch of helpers here, and that's good. Let's just sort of go ahead and sort of create the other methods that we're going to need. So the final helper that's going to be helpful for us is, and I'm going to make this public just so we can see how the heap works, but you wouldn't actually necessarily need this, although you could have this, is we're just going to return the heap array because I've made it a private variable with encapsulation in this class here. we can just go ahead and we can just return this dot heap array here. And that will just allow us to look at the heap array while we're creating and implementing the insert and remove and heapify functions and swap functions and stuff like that. So basically, let's start with the insert. And the insert, it's basically you got two different types of heaps, right? So you got the min heap and the max heap. And I actually might just create those classes because it's going to give us an understanding of what we're trying to get to. So we're going to create the min heap, which just extends the heap. And then we're also going to have a max heap, which is the same sort of thing. So the max heap is also going to extend that. Now, I'm going to have this compare function here. And what compare does, the reason I'm having that separately, so I'm going to have it on the max heap as well, is because in the min heap, you're comparing to see if the child is less than the parent. And you're comparing in the max heap to see if the child is greater than the parent. And if it's equal, it doesn't matter because it could be in either spot. So basically, I'm just going to take the first value, which is a number, and the second value, which is also a number. And I just want to determine, whether or not the first value is less than the second value. Because for a minimum heap, the first value that I'm going to pass in here into this function is, is going to be the child, and we're expecting the child to be less than the parent, in which case they'll return true, but our heap can get out of order, where they'll return false, and if that is, we'll need to heapify things to be able to make everything back in line. And then this is basically the exact same thing, but you're trying to see if the parent's larger than the child. And we can make use of that. So when we, in the base class, we can use that depending on which heap we're using. The other thing I want to do here is I'm just going to have sort of a wrapper. I'm going to get the min value because sometimes we want to, in a min stack, one of the purposes of having it ordered like that is you can easily look up the minimum value because it's just going to be the first element. And I'm going to return this .peak top, which we haven't actually created yet, but we will. And that's going to do exactly as the method name suggests. And I'm also going to have that in the max heap, but in the max heap, it's going to return the maximum value. So that's just sort of like a wrapper over the top. So basically where we want to get to is we want to be able to create a min heap, insert into it, get the min value, get the remove a value, and check everything's all working. And then we want to do the same thing for the max as well. So now that we have that compare method, we can actually sort of start to work on the methods that we really want. So basically, we need the ability to swap if the elements are out of place. So let's actually go ahead and just create that. So that's going to be quite simple. We can just have like a private method here, and I'm just going to call this swap. So you're going to get past the first index, which could be the child, and then you can get the second index, which could be the parent, or could be the other way on. And this doesn't return anything, but it does a setting operation. So we can say that we can take the heap array, and we can take the index 1 here, and we can use this array destructuring syntax, so we can just do this in a one-liner. And it's not too bad without temporary variables. because each of the indexes, when you get the element, is just a primitive number, so we're not referencing an object here. So when we're doing the recreation, it's not taking too much data up. So this is perfectly okay. And then I'm just going to swap these around here like this. So index 1 and index 2. What's happening here? So this heap array index 1 and this heap array index 2 is going to be equal to this heap array index 2 and equal to index 1 here. I'm not sure why I'm getting this semicolon here. Oh, did I forget? No, I didn't forget something. Let's see here. Yeah, I'm not sure why that's happening. That might error later on. Let's have a look. If it is, I'll just make a temporary variable. Actually, I might just make a temporary variable. Because that's sort of strange. I don't know if that's just prettier interfering or not. This heap array. So let's create a temporary variable first. It's equal to this heap array index 1. And then we can say this dot heap array index, this heap array index 1, we're going to set that equal to this heap array index 2, and then this dot heap array index 2, we can set that to that temporary variable there. So that's just another way to swap it. I don't know what was happening there. Probably will be obvious later on. There was some sort of syntax error or something like that. But that's the ability to swap two things. So basically all we've done, since we're implementing this in arrays, we've just swapped the values of two indices in an array. So with all of that, we're in a good position to actually implement our functions here. And actually, I might just quickly do a peak top method here. So I'm just going to have a protected method here, peak top, and it's protected because we're extending it in the min and max heaps. So this is going to be either a number or undefined. And essentially, if this heap array, if it has a length equal to 0, we're just going to return undefined because there's nothing to look at. Otherwise, we're just going to return the first element. So we can just do it like that. Okay, so now we want to actually get to the more interesting stuff, which is inserting and removing. So let's start with inserting. So let's just have a public method here. And you don't have to use the keyword public, but I'm just doing it because I got protected and private, and it just sort of keeps it consistent here, but it doesn't really matter. Basically, we're going to have some sort of number and we want to insert it into our tree, into our heap. So the first thing we do is we just simply, for the heap array, we can just push the value. And that's going to put it right at the end there, which isn't necessarily going to be in adherence to the heap property that we have. So what we do is we just say let the index equal to this dot heap array dot length minus 1. So that's just going to give us the length of the array, and then subtract 1 from that to get the last index. And then what we can do here is we can have like a while loop. So while, and let's think about this for a second. If we're inserting something and we insert it to the end, we want to, firstly, we just want to check that to see, that a parent exists, because if you're at the very top of the tree, you can't go any further. But then we want to compare that last element to the parent element, and then we just want to make sure that it's in adherence with the heap property. So we made that compare method here. So for the minimum heap, you got this one here. For the maximum heap, we got this one here. Basically, in the minimum heap, the child should be less than the parent, and it's the other way on for the max heap. But it's good to just keep one in mind when you're thinking about this. I'll sort of think about it for the minimum heap, and then the maximum heap logic just comes naturally just by inversing that comparison there. So basically, we need to check that we have a parent for the given index there, and that the heap array, and I could be using get heap array in all these spots because I've added this helper method here, and probably that would be more in line with the OOP way of things of doing it. I'll sort of tack this on at the end just as a helper, just to see things. But yeah, it's just up to you really. So this heap array here, actually before we do this, we want to check, we want to do that comparison there of the heap property. So it doesn't matter which one we're on. If we're on a min heap, we're enforcing the min heap comparison. So basically we could have something like this, where since the index is going to be in the end there, that's going to refer to the child. So we want to check that the child is less than the parent index. So we have that helper method that we created before to get the parent index from the index. And that's just based on, those mathematical facts to do with the binary tree. Okay, so we don't actually have this on the so what we'll do, since we're extending this on the subclasses, we're going to need to create a abstract compare function, which just takes the first value, which is a number. And I'm just going to have this signature here for this. So that's the Boolean here. So when you extend this class, we're able to make use of this signature here. So that means when you're calling the method on the instantiated class that extends it, then you'll have access to that method here on this class. So we're able to check for that heap property, and as long as the heap property is respected, this is checking the other way on. So if in the case of a minimum, if the value isn't respected, we're going to continue to do something until we get into a spot where it is respected, and then we're going to exit the loop. So just to make that clear, what we can say is we can get the parent index, and we can just get that by getting the parent index of the index here, and we can make use of the swap method here. So basically, if the child becomes greater, if the child becomes less than the parent, in the case of a min heap, we want to swap them. So we can just swap the child with the parent, and that would make the parent smaller than the child. So what we can do then is we can just say, well, since they've been swapped, which would then adhere to the heap property for that particular those two particular nodes, we can just set the index up higher to the parent index, and then we'll do the checks again. So basically, if that has a parent, then you do the comparison again, and then if that parent has a value that's greater than the grandparent, then it will fail the test, and it will just completely it will start repeating through this while loop until you get into a position where the value has been inserted, and then all of the parents are in adherence to the heap property, depending on what that is for the min or max. So that's actually how we insert something. And now we just need to think about how we would remove something. So let's have a public method here, and I'm going to call it remove, which is just going to take a value, and we're going to have this here, and this whole thing, we're sort of making the assumption that we're not going to have duplicated elements, otherwise we'll just need to have a couple of extra steps there. But just to keep things simple, we want to find the index of the value we want to remove, so we can actually just look at our heap array and then just get the index of that. And index of, if nothing's found, it returns -1. So basically, if the index to remove is equal to -1, well, then we just return, because that value wasn't in the array or heap to move. So then what we want to do is, once again, we want to, if we're removing something, basically we want to do some swaps. So what we want to do precisely is we want to swap the index to remove, and we swap that with the last element. So we sort of explained this before, but just to reiterate, if we swap the element that we want to remove with the last element, what that allows us to do is it allows us to just pop off the stack or the heap, which is an all of one operation. Now, obviously, that means that the thing here could be in the wrong spot. You could get lucky, and you could be removing the last element. So what you say here is, if the index to remove is less than the heap array length, then we'll do something. Now, if the index to remove is the last element in the array, and recall that we've done this pop, so that would remove one more. If that was true, then you wouldn't have to do anything, because you've just, removed it, right? So, but if that isn't true for any other position, we want to call heapify. And heapify is the final thing that we'll create. And we just pass in the index to remove. So basically, the way heapify works is it just, obviously, when we do this swap to leverage this all of one operation on the pop there. It's going to screw up the the position that got swapped, like, you know, the last element that made it there, sort of thing. That got swapped with that position that we're trying to remove. But it's okay because we got this heapify method, and the heapify method's going to leverage the fact that we got a binary tree and this heapify heap property adherence, and that's sort of going to optimize the time complexity associated with actually performing such an operation. So let's just go ahead and create that. And this is sort of like the climax of the heap data structure here. So basically we're going to take the index for the position of the node of the value in the tree. Now it's not going to return anything, but what it will do is it's going to set some things, right? So basically we're going to have a while loop here, and I'm just going to say while true because we're just going to put a break condition in later on. So basically what we want to do is let's just first set the index that we're comparing. We're just going to set that to the variable compare index equals to index. And we're doing that because basically that's going to be our break condition. So we're going to keep looping through, and then that's going to equal index, and then we can break. But let's just make use of some of the methods that we've created so far. So we've got the left child index, which we can determine by making use of the get left child index here. And then we also want the right child index, which we can make use of our get right child index here. So basically, and let's just save that to format things. If you get into the situation where, well, firstly, if you have a left child, you want to be able to know that you have a left child before you sort of try and change or do a swap with it. Or, you know, you make sure that it adheres to the heap property. If that's true, so you have a left child, and you make sure that it adheres to the particular heap property that you're on. So to do that, we can just say this dot heap array and get the left child index here as the first element, and the second will be the heap array with the compare index. So basically, if this is true, what that means is, well, you have a left child, and this left child is less than this value here, in this case here. And if that's true, basically we want to be able to break. So basically we want to say we'll set the compare index to the left child index, and then basically down here we're going to have this break. So if the compare index is equal to the index, we can simply break. So let's just think about this once more for the minimum heap case. And obviously we've been thinking about this in the context of minimum heap, but all of the logic applies to the max heap. It's just good to think about one to make sure it adheres to that those rules, and then it'll work for the other ones as long as you implement the code correctly. But just as like a thought exercise to make sure things are checking the boxes, we can just say, right, if you have your heap and something's in the wrong order, you can sort of look at that index of the, say, the removed element, and you can compare that to the children, because you're trying to determine if it's adhering to the heap property. Now, if it isn't adhering to the heap property, something's gone wrong. And then what you would need to do is you would need to do a swap. So you would swap the index with the compare index. And then in the next iteration, the index is going to be equal to the compare index. And actually, I'm so far in, I might as well just finish off this for the right side and then do the overview of that again. Because basically, it's going to be the exact same thing on the right side, right? So if the right child has the index, and you have the right child index there, then you can just sort of increment the compare index. So I just want to quickly go over that. Basically, if you got something in the wrong order, it's going to, like, these won't be true because it means that your compare index hasn't sort of aligned. You know, the heap property's been violated. So if that's, if that's the case, then you just swap them. But you could get into a situation where it's, you haven't just removed something from the bottom layer or the second layer from the bottom, you remove something way at the top. So you actually need to check it for like the whole chain. So that's why we have this while loop. So if something's in the wrong spot, you swap it, and then you sort of change the index. So the compare index, right, is firstly it's going to be equal to the index. And then let's say it's wrong in the first case, you're going to swap the things around. So you swap the index with the compare index. We're sort of thinking, well, since it is in a heap except for that particular spot, we're sort of thinking, well, the child, either the left child or the right child, if that does, in the case that it does satisfy the heap property, then we can sort of change that compare index to either left or right child. And then eventually you'll get into the spot that the compare index will be equal to the index, and then you can just sort of break. So when everything's in order, there's no need to swap things around. So yeah, that's essentially the heapify property here. So let's actually go ahead and make use of that and just sort of check that we haven't made any errors and everything's sort of behaving as we would expect it to behave. So let's just do some example usage here. So let's create a min heap. And that's just going to be equal to a minimum heap here. And then what we're going to do is we're going to take the min heap. Oops, min heap. Oh, good. We're going to take the min heap variable that we just created. And then let's just insert 10, for example. Let's do a few more inserts. So let's insert the value 15, the value 5, the value 20. And then something we want to do is we want to check the minimum value. So let's just say we'll console log the min heaps get min value here. So this should give back 5. And then let's say we want to just see the array just to make sure that everything's still in order and all good. We can get the heap array, and then let's say we want to remove the number 15 here. Now that should, when we console log out this again here, this should give us that minimum heap but without the number 15. And let's do the exact same thing but for the maximum heap as well. So these values here. I'm just going to change to max heap here, and then this one here I'm going to set that to max heap, and then this time this should be 20. So just a small typo, you probably caught this, but this compare index here, this should be the right child index here. Also made a small typo here. This should be get heap array here. So let's just check that in the few spots there. Let's just save that, because that method wasn't running. So now we can see that we insert 10, 15, 5, and 20. And then we want to get the minimum value, so that first value is 5 there. Then we get the whole array, which is 5, 15, 10, 20. So the root is 5, the left child's 15, the right child's 10. And then the left child of 15 will be 20, so that follows the minimum heap property where the child needs to be less than or equal to the parent. Then we go ahead and we remove 15, so that gets removed there, and then it still follows the minimum heap property. And then we do the similar sort of thing for 20, so for the max heap. So we see that the maximum value would be 20 there. The whole heap looks like that. And then if we remove 15, it still preserves the max heap property where the child needs to be less than the parent or equal. So that's the heap data structure and the minimum and maximum heap and all of the operations. Let's go ahead and see how we can use this in an algorithm question.